big D, it stands for detector. So detector detects 100% lights to be emitted. None of them are observed. So now once detector detects that, detector is connected with the computer, and that is also connected to the monitor screen, where we can see a graph forming. Now if I do the graph, how it will look like? It will look something like this. If I do the graph like this, in the x-axis we are talking here about the percent emittance, the percent emittance, that is the percent emission, and this is in the y-axis. In the x-axis we have the wave number, which is in inverse centimeter, and we can guess it from, let's say here is a 4000 at this point to, let's say here is a 500 inverse centimeter. Okay, so this is the idea, and here we have the 100% emission at the top, and at the very beginning there is a 0% emission. So this is the emission scale. So what we can see here, as all of this light is passed, none of them observed, so we see 100% emission here at the very beginning with 1 Hertz. Okay, let's say for this understanding we simply do this calculation in Hertz, the frequency we are talking about. So at 1 Hertz we see 100% emission. Okay, now let's change this frequency of IR light that's going in. Now let's say the frequency we go with 2 Hertz. What will happen? We know that this C and O, this double bond, they stretch in the frequency of 2 Hertz and they wag in the frequency of 4 Hertz, right? So as the frequency of this IR hitting this molecule matches with the frequency of the stretching between the carbonyl carbon and oxygen, that is also 2 Hertz, this compound will absorb most of the light, most of the IR spectrum, most of this light will be absorbed by this formaldehyde there, and very little will pass, very little. Theoretically it should absorb all the light because it will get the energy source and will start stretching itself, but sometimes, due to the practical experiences, you can see that some part of this UV radiation is also passed to the detector, but detector detects very less amount, which acts as a background noise, we can tell. So for the 2 Hertz, if you look at here, for the second 2 Hertz, you will see a sharp drop. You see a drop in the emission. Now let's go back to the 3 Hertz. If we now emit the 3 Hertz, again none of this compound, they have a 3 Hertz frequency in anything. So again they are not going to absorb 3 Hertz, they are going to leave it away, so most of the light will be emitted. So again in 3 Hertz you will find a steady, you have 100% emission. Now finally it goes with the 4 Hertz. Once it again fires it in the 4 Hertz, the frequency of the IR radiation, that is 4 Hertz, is again to inspire the wagging movement. So most of it will be observed, very few will be emitted, act as a background noise. In that case also we'll see a drop, 4 Hertz. So by this fashion, what we can see in this graph, this kind of graph you will see, it's very common type of graph for IR spectra. You will see a lot of things down, like normally it's 100% emittance, but then you'll see the absorbance. This drop in the emittance means absorbance. That's what we're talking about. Absorbance. Whenever absorbance, that means this molecular compound that we are testing is absorbing the IR, and that specific frequency that matches the frequency of stretching and wagging, or the vibration of that functional group. Now this vibration of the functional groups are specific for specific functional groups. For this carbonyl, this will be fixed 2 Hertz for this stretching, 4 Hertz for wagging. Now remember, it also varies with the situation of this molecule and how other groups are placed. It's not that simple. Here we draw a very simple example. multiple groups are present, and it will have influence for the presence of other groups as well. And secondly, it also depends on the length between the bonds that are present between the two components here, which is in this case carbon and oxygen. As it's a double stranded bond, and also if it's a double bond, the stretching movement and vibration will be different. The frequency of vibration will also be different. If it's a single bond, if it's a triple bond, it will be also changed. So based on the number of bonds, it will also vary. The length of the bond, it will also vary. So all these things matters a lot, and also the presence of other groups also determine what kind of absorbance it will actually have. So that in a sense of whole process. So now if you look at some of these graphs, you will see 100% emittance, and in the x-axis you will probably find a lot of data, like in the wave number. The data in the wave number means it will be like centimeter inverse value of the wave number, and you will see like 4000 here and 500 here. So this is going to give you an idea about the array. It's not about, we're not talking here about like let's say, let me just erase that. Let me talk about let's erase this one, and let's say we are talking about the graph and the data about the wave number for the infrared. And wave number we're talking here that 4000, and here we have let's say 500 only, and here we see the different emission in the y-axis. So what we see here, if you look at very carefully, you will see a lot of different peaks coming in, going down, like peaks like this, and at the end, after a specific point, you will see something like that. What is that? I'm going to explain in a moment. There are two segments you can form by looking at any of this IR spectra data. One, it is completely based on the wave number that we are looking for this wavelength. The wave number that we are looking for, it belongs to it starts from 4000 to 1800, that range, and then another range from 1800 to 500. Mostly from 4000 to 1800, that area of the data, it represents the functional group. Mostly it represents all the specific basics functional group that we know of in the organic chemistry. All those functional groups, they range from this 4000 to 800. But now if we go from 1700 to 500, that range, that is mostly filled with very tiny modification among those functional groups, and that is very specific to the specific molecules. So that region of the spectra is very important, and the resolution is also very important at that end of the spectra, because that is known as the fingerprint region. This first area is known as the functional group region, because it will give you the idea about the functional group of the chemical compound, which will be very important idea. But the second one will give you the idea about the exact type of functional group you're talking about. It's going to give you the idea about the exact atom present near each other. That is known as the fingerprint region, because this fingerprint region, why? Fingerprints are unique for all of us. So fingerprint region means this region will be unique to all those different chemical compounds. That is the idea. So for getting this, if we get a graph like that, and if you get an idea about the functional group and fingerprint, along with those two things each other, it's going to give us the idea about what kind of chemical compounds we are talking about. And that's what IR actually do. IR spectroscopy will help us to get the idea about the molecules different groups, and the presence of group will be very beneficial for us to calculate what kind of molecule we are talking about. That's all about infrared spectroscopy. I hope you understand this process. If you like this process, please hit the like button, subscribe to my channel to get more videos like that, and definitely share this video with your friends. Thank you.